Chapter 8, Section 1, Sequences and Sum Notation.
So sequences and series notation. So we're going to cover what is a sequence, what are sequences, describe recursively defined sequences, then look into the partial sums of sequences, and then sigma notation for sequences. Okay. So roughly speaking, a sequence is an infinite list of numbers. The numbers in the sequence are often written as a sub 1, a sub 2, a sub 3. The dots mean that the list continues forever. Okay, so it's a list of numbers that could be, let's look at some examples. So for example, it could be the numbers 5, 10, 15, 20, 25, right? So clearly we're adding 5s every time. It could be a list where there is no reasonable pattern, right? It could be something like 3.12, 7.98, then negative 3.21, then positive 21.19, right? So here's this list, and there is no reasonable pattern that I can think of. Maybe there is some reason for this madness of how you go from one number to the other, but at the moment there doesn't seem to be one, and that's okay. A sequence doesn't have to have a pattern to establish how you go from one to the other. It's simply a list of numbers. That list goes on forever, so we indicate these little dots to show that, oh, this keeps going. It's not just going to stop there. But what's important is that the order matters. It's not just that these numbers are on the list. It's important that this one is the first number on my list, and this one is the second number on my list, and this one's the third one, and then this one's the fourth one, right? So the order of the numbers makes a difference, and then often these are separated by commas just to make sure that it's clear that one number is ending and the other one is beginning. Okay, so there is an order to them. So when we refer to a list, and then we want to talk about the first one on the list, right? How do we use math language to indicate that it's the first one on my list, the second one on my list? What if I want to talk about the third one on the list, blank third? So that's where we introduce these variables, and it could be any letter, but A is a very popular one to use. And so A sub 1 is just indicating that it's the first value on my list, right? This little sub-index here, this little 1, is indicating it's the first one on my list. A sub 2, A sub 3, and so on. Right? The nth one on my list is the a sub nth one. Right? We can also use any other letter, b sub 1, b sub 2, b sub 3, dot, 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 dot. Right? And then because I'm using a different letter, this would be used to note that this is one sequence and this is a different sequence because I'm using a different letter, different variable to identify it. Good? Good? Okay, so obvious, like I said, there doesn't have to be a pattern from one number to the other, or maybe it's an unknown pattern, and that might be what we're trying to figure out. How do we figure out a pattern to these numbers? But obviously, when there is a pattern, especially an easy pattern or a well-established pattern, then there's more interesting things that we can do with it, right? If there is no pattern at all, then we're kind of stuck. There's really not much else we could do. But if there is a pattern, like there was one here, then we can work with that and come up with a formula that helps describe those patterns, right? So in this case, we were going from 5 to 10, 10 to 15, 15 to 20, right? So it looks like we were adding 5 every time. That's one way to look at it. Adding 5 every time. Add 5 every time to get to the next one. Okay, that's one way to look at the pattern. The other way to look at the pattern is to try and look at the relationship between the location, which is these little numbers, right? It's the second one on my list. It's the third one on the list. It's the fourth one on the list. So look at the relationship between the location and the value on that list. And so if you notice, the second one on the list, if we multiply it by 5, we get 10. The third one on the list, if we multiply it by 5, we get to 15. The fourth one on the list, if we multiply it by 5, we get to 20. And so the relationship is that the location on the list, right, when we get to the nth one on the list, then the value that goes on there is 5 times n. Good. And so that's where this little formula comes from. So some sequences can be expressed by a formula like this. And when they can, that's very useful. Right? We can use that formula to find different values on my list. So I can say, find the 113th number on the list, and I know that that's pretty easy. It's just 113 times 5. That'll be the one that's on the list. Any questions so far on what a sequence is? A sequence is a list of numbers that goes on forever. And the order is important. We list them. The first one on the list, the second one on the list. We often say, because they're in order and we can count them, the first one, the second one, the third one on the list, we often say it's a list that's indexed by the natural numbers or the counting numbers, right? So that's another way to describe what a sequence is. A sequence is a list of numbers indexed by the counting numbers. Right? And by indexed, we mean this, that the counting numbers, we can identify them in a particular order. The first one on the list, the second one on the list, third one on the list, the fourth one on the list, and that just goes on by forever. Good. Any questions at all on what a sequence is? No? No. Okay. So here's some more descriptions on it. So any ordered list of numbers can be viewed as a function whose input values are 1, 2, 3, and whose output values are the numbers on the list. So we define a sequence as follows. Right? So a sequence is a function A whose domain is the set of natural numbers. The terms of the sequence are the function values A1. So this looks a little weird, right? We're used to using the letter F as a function, but here they're using the letter A as a function. Right? So it might look a little weird that way. You can also think of it as f of 1, right? Because we're used to seeing a function in terms of the letter f. F of 1, f of 2, f of 3, ... right? And so f of 1 means that the first one on the list is whatever this output is. The second one on the list is whatever the output of this function is. The third one on the list, and so on and so forth. Right? So like maybe, for example, if f of n equals to n squared plus 1, then this is the formula that's describing my sequence. So now I can plug in a 1 for n equals to 1, and I would end up with 1 squared plus 1 for the first one on my list, which is going to be equal to 2. And then 2 squared plus 1, which is going to be equal to 5. 5. Then the third one on the list, 3 squared plus 1, is going to be equal to 10, comma, and then ... And then it's kind of silly that we use the same letter, but then we'd say the nth one on my list would be n, f of n is out there, and then it is n squared plus 1, so we could say, comma, n squared plus 1. Good. Questions? No. Okay, so this notation of A1, A2, A3, this notation is the same as f of n. And also, instead of writing A of n equals to n squared plus 1, right, same thing as that one, then we also often adopt the new notation of A sub n, like this, instead of A of n. Good, which is what they describe here. Good. So A sub 1 is the first term on our sequence. The second term is A sub 2, the third term is A sub 3, and so on and so forth. Right? Not every sequence has a perfect little formula to describe it, but like I said, it's very useful when there is a nice formula and we can do more work with it when we have the formula. Sometimes the exercise will be to find that formula, if you can. Good. Any questions? So far, we're good? Good. Okay, so here's some examples. Find the first 5 terms and the 100th term of the sequence defined by each formula. Okay, so remember, this is a function. This is a function. Oh wait, why is this thing highlighted? This is a function where the input is the counting numbers. So if you want to find the first one on the list, you got to let n equal to 1. If you want to find the second one on the list, you got to let n equal to 2, and so on and so forth. Okay, so let's create a little table here and find a few of these values. Let's get rid of that thing there. So when n equals to 1, this first one will lead to 2 times blank minus 1. This next one will lead to, let's call this A sub 1. C sub 1 would be blank squared minus 1. And then T sub 1 will be equal to blank over blank plus 1. And R sub 1 will be equal to -1 to the power of blank all over 2 to the power of blank. Okay, so here we're letting n equal to 1, so it'll be 1 there, a 1 there, a 1 there, a 1 there, and a 1 there. Okay, so this will be 2 minus 1, so a sub 1 is going to be equal to 1. And then c sub 1 would be equal to 0. 1 squared is 1 minus 1 is 0. This becomes 1 over 2, so t sub 1 is equal to 1/2. And then r sub 1 is equal to negative 1. Oops, I forgot the other one here. 1 becomes negative 1 over 2, so negative 1/2. Good. All right, so we found the first value in each of these sequences. Now we've got to move on to n equals to 2. Find the second value. Good. Then we have a sub 2, we have r sub 2, we have t sub 2, r sub 2 equals, okay, and this one was 2 blank minus 1, blank squared minus 1, blank divided by blank plus 1, negative 1 to the power of blank all over 2 to the power of blank. And now we're going to let, well, I should have put this in red, I guess. N equals to 1, and n equals to 2. So we'll have a 2 there, 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 and a 2 there. Okay. So here we'll end up with a sub 2 equals to 4 minus 1, which is 3. C sub 2 equals to 4 minus 1, which is also 3. T sub 2 will be equal to 2 over 3. And R sub 2 equals to positive 1 over 4. Good, 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 good. We'll squeeze in one more, and then we'll be close to where we want to be here. I think we can guess the rest. So n of 3. So we have a sub 3 a sub 3 is equal to 2 times blank minus 1. C sub 3 is equal to blank squared minus 1. And T sub 3 is equal to blank over blank plus 1. And R sub 3 is equal to negative 1 to the power of blank all over 2 to the power of blank. Squeeze it in a little bit. Okay, so that'll be a 3 there, 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 and a 3 there. So a sub 3 is going to be equal to 6 minus 1, which is 5. And then c sub 3 is going to be equal to 9 minus 1, which is 8. This would be equal to 3 over 4. T sub 3 will be equal to 3/4. And r sub 3 is going to be equal to negative 1 over 8. Good. Okay, so we did the first 3. So let's write down those, and then we can just finish off the rest. I think we can do those patterns. So let's copy this one. So a sub n equals to 2n minus 1. So we have that the first one is a 1, the second one is a 3, and the third one was a 5. The fourth one will be a 4 in here. That'll be 8 minus 1 is 7. The fifth one will be a 10 minus 1, which is 9. And also I begin to see a pattern here that it goes by 2s. It's all the odd ones. 1, 3, 5, 7, 9. So this is a really popular formula which identifies the odd numbers. List of odd numbers. Right? The odds are 2n minus 1, where n is the counting numbers. Good. So we also want to find the 100th term, and that's easy. All we have to do is plug in a 100 in here. Right? So if we plug in a 100 in there, we end up with 2 times 100, which is 200 minus 1 is 199. Dot, 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 and then this would be 199. Good. Questions, 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 questions? So that's good enough for an answer, or you can also sub-index them. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, dot, 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 and this one was A sub 100. We're good? Questions, 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 questions? Okay, let's look at B. So now B, which was C sub n equals to n squared minus 1. Then the first one was a 0. The second one was a 3. The third one was an 8. Come over here. Okay, the fourth one, that's going to come from putting a 4 in here. That's going to be 16 minus 1 is 15. The fifth one will be 25 minus 1 is 24. So here's the first 5 terms, 1, 2, 3, 4, 5. And they also won the 100th term. 1, 2, 3, 4. So the 100th term is going to be equal to 100 squared. So 100 squared minus 1. So that's 100 times 100 is going to be equal to 1 with 4 zeros minus 1. 1 with 4 zeros is 10,000. So this is going to be 9,999 is the 100th term. Right? And again, you could label them if you want. The first one on my list, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, dot, 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 over a sub 100. Any questions, any questions, any questions? No? Okay, C was n over n plus 1. Okay. And so we saw from up here that the first one was a half. First one was 1/2, then 2/3, then 3/4. So 1/2, and then 2/3, then 3/4. And we start to see a pattern really, but then it's not so hard to plug in the rest anyway. So there's the 1, 2, 3. So with 4, we'll end up with 4 over 5, and then 5 over 6. Good. And then dot, 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 and then the 100th one will be 100 divided by 101. Right? And so this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and finally a sub 100. Good. Last one, D. The equation was r sub n. R sub n equals to negative 1 to the nth power divided by 2 to the nth power. Good. So we saw that when we put in a 1, this negative 1 to the power of 1 was just negative 1, and this stayed as a 2. So the first one on my list was negative 1/2. The second one on the list, the negative 1 raised to the power of 2. Negative 1 raised to an even power becomes a positive. So this became 1. And 2 to the power of 2 is 4, so this became positive 1/4. The next one becomes a 3. Negative 1 to the power of 3 becomes negative 1 to the 8th power. Then positive 1 to the 2 to the power of 4. So this is just going to be powers of 2. 2, 4, 8, 16, negative 1 over 32. Right? So I can just kind of see the pattern that's being established. And notice that this part, the minus 1 to the nth power, what it generates on our list is that it alternates between a negative number, a positive number, a negative number, a positive number, right? It alternates between signs when you use this. Good. Good, 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 good. Okay, so this is the first one on my list, this is the second one on my list, this is the third one on my list, this is the fourth one on my list, this is the fifth one on my list, and then comma, dot, 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 and then I want the 100th one on my list. Negative 1 to the power of 100. Right? Whenever the exponent is even, it's just going to turn out to be a positive. And whenever the exponent is odd, it turns out to be a negative 1. Good? So this is going to be positive 1 over. Now, the denominator is 2 to the power of 100. Right? So when it's 2 to the power of 3, you're expected to expand it out and actually multiply it. But very quickly, these numbers get really, really, really big. Right? So the general guideline is that if an exponential number, when expanded, when you multiply it, it turns out to be a number that's less than 1,000, they want it to be written out, right? So this is, if you look in solution manuals or something, you'll see it written out like this. But once it reaches a value that's over 1,000, then people really embrace the convenience of expressing the number as an exponential, so we would leave it like that. Okay, so this is the 100th value on my list. Any questions at all? No questions, no questions, no questions. No questions, no questions. No, no, no. Okay, let's see what the author did. Basically the same thing. To find the first 5 terms, we substitute n equals to 1, 2, 3, 4, and 5, and then 100 to find the 100th term. Okay, so that's basically what we have as well. So some of your homework will be just this easy. A formula is given, find the first 5 terms, find the 100th term, find the 78th term, something like that. So you just have to plug it in and calculate it. So that part's easy. But then, of course, we throw in some twists and make things a little tougher. What if the sequence is given to you and instead they're asking you to find the nth term of the sequence. In other words, find a formula for the sequence. Good. So in order for us to find the nth term, it's the same thing as saying find the formula of the sequence. So for part A, luckily these aren't too bad. If you see a fraction, my recommendation, and these aren't rules that will always work, just sort of guidelines that usually work. But if you're given a sequence and you're asked to find the formula, the nth term, I would break it down into two separate parts, figuring out a formula for the numerators and then figuring out a formula for the denominators. Now when we say a formula, remember that the nth term refers to the location on the list. So what I want to do is think about this. I have 1/2 here, and what I want to do is I want to take this 1 and I want to somehow plug it into a formula, and the output of that formula should be this, right? I want a function a of 1 that equals 1/2. Right? I want to be able to plug in a 1 and the output is 1/2. Good. And at the same time, I want that formula to work out such that if I plug in a 2, a sub 2, that 2 right there will result in 3/4. Right? A of 2 should be equal to 3/4. Good. And so on and so forth, and so on and so forth. So this should be 5/6, and then the next one should be 7/8. Right? So one formula that generates these 4 terms when we plug in these their corresponding location values. A sub 3 and a sub 4. Okay, so how do we get 1 to map to 1 and 2 to map to 3? So I would break it down between the numerators and the denominators. And so if we notice, the numerators are all the odd numbers, 1, 3, 5, 7. From that, my best guess, just looking at the pattern, my next guess is that the next one's going to be a 9 in the numerator. Good. And then in the denominator, it looks like they're all 2s, powers of 2, or even numbers. 2, 4, 6, 8. Right? So they're not powers of 2 because 6 is not a power of 2. So we're just adding 2 every time. So just all the even numbers. Right? So my very best guess is that the next one is going to be 9 out of 10. Right? So by breaking these down, it seems to me that it's going to be the odd numbers divided by even numbers. So looking at just the numerators, we saw earlier that this is a way of describing the odd numbers, and this is a way of describing the even numbers. Right? So when n equals to 1, right? So for this, you want to do a lot of guessing and checking. Try an equation, kind of guesstimate what the equation will be, and then come back and make sure it makes sense. Right? So when n equals to 1, we'll end up with 2 minus 1, that's 1. And when n equals to 1, that equals to 2. So we end up with 1/2. Right? That does make sense. N equals, let's put it over here. Check. When n equals to 1. When n equals to 1, we end up with 2 times blank minus 1 all over 2 times blank. And if n equals to 1, we end up with 1/2. Good. When n equals to 2, we end up with 2 blank blank minus 1 all over 2 times blank. And this is a 2, this is a 2. That makes it a 4 minus 1 is a 3 over 4. 3/4. And that does do that one. That gives you the second one on my list. Good. Any questions, any questions, any questions? So it worked out. This is the formula. Any questions, any questions, any questions? No? So when you see fractions, very often it works to try and break it up, to figure out a pattern for the numerator, a pattern for the denominator, and then write down that fraction. Now if you want, once you have that pattern, then you can also just kind of manipulate that algebraically and get a different expression. So you could also rewrite this as 2n over 2n minus 1 over 2n, which then reduces to be a 1, which gives you 2n is equal to 1 minus 1 over 2n. I don't know, if you like seeing it this way better, then that's fine too. This will also give us the same result. Right? Again, you can guess and check. If n is 1, we end up with 1 minus 1/2, which is half. Right? When n is 2, we end up with 1/4. 1 minus 1/4 is 3/4. That also works. Right? So here's another way of expressing the same answer. Any questions, any questions, any questions? No? No? Okay, so 2 different ways of expressing the same answer. This is all for part A. So this was all part A. All right, let's do part B. Part B has -2, +4. So we have -2, then +4, then -8, then +16, then negative 32, and so on and so forth, so on and so forth. Okay, remember, our mission is to find a way to map the fact that there's a 1, and it's the first one on the list. So I want to do something to the 1 so that I end up with a negative 2. And then I want to do something to the 2. The 2 is the input to my function, such that when I do something to it, the formula results in a 4, and then 2 results in a negative 8, and then 3 results in a negative 8, and 4 results in a 4. Okay, well, it's not hard to see that these are the powers of 2, 2, 4, 8, 16, right? So it has something to do with 2 to the power of the index, the counting number, the location on the list. And then the only thing that we have to be careful about is these signs. It alternates signs between a negative there, then a positive, and a negative, and a positive, and a negative. Good. And we saw in a prior example that one way to get that is to have the negative 1 to the power of n formula, and then just confirm that it matches all the signs. So when n is 1, we'll get a negative. That makes sense. When n is 2, we'll get a positive, because negative 1 to the power of 2 is equal to a positive. Okay, so that part matches. And so now that we multiply by 2 to the power of n to get the constant. Right? So here's my guess for the formula. Oh, I already used a over there, so let's use a different one. How about b? b sub n is this one. Right? So we guess and check. This is what I think it'll be. And now I check it. Check. When n equals to 1, I end up with negative 1 to the power of blank, 2 to the power of blank. And that'll be a 1 there and a 1 there. So that equals to negative 2. Okay. When n equals to positive 2, then we have negative 1 to the power of blank and 2 to the power of blank. So we get a 2 there and a 2 there. Negative 1 squared is positive 1. Positive 1 times 2 squared is 4. So this will be equal to 4. Okay. N equals to 3, you get negative 1 to the power of blank and 2 to the power of blank. Put a 3 here. And so now again, this becomes negative 1 times 8. So this becomes negative 8. Okay, so it's confirming that it is giving us the values we wanted. Any questions? So it's a little trickier when you're trying to find the formula. See what the author did, probably the same thing. We notice that the numerators of these fractions are the odd numbers, the denominators are the even numbers. Even numbers are of the form 2n, the odd numbers are of the form 2n minus 1. The odd number differs from an even by a 1. Right? So once we have all the even numbers that are 2n, we just subtract 1 and we get to all the odd numbers. Good. Okay, so that was a sub n equals to 2n minus 1 over 2n. That worked out. And then same thing for the other equation. Noticing that their powers are 2 and that they're alternating signs gives us this, and then we kind of guess and check it and confirm that that is the equation, the formula for it. Any questions? Any questions so far? Okay, so as I mentioned before, there doesn't have to be a pattern. It's nice when there's a pattern, but in order for it to be a sequence, there doesn't have to be a pattern. And sometimes maybe there is a pattern, we just don't know it yet, right? Maybe we observe something in the universe and it's pumping out weird numbers, and we don't know if there's a relationship between them, but maybe that's the whole point. We're trying to figure out how do we get from one number to the other. So in some cases, there is a nice, pretty formula for it. And in some cases, there might be something that we describe as a recursive sequence. This is a sequence which is described by the values that came before it on the list, a finite number of values that came before it on the list. So for example, well, you got to get the thing going. So let's say that it just starts at 3, right? So that part is given. Let's say the first two numbers are given, 3 and I don't know, 3 and 4. Given and given. You got to get the thing going. So a sub 1 is given and a sub 2 is given. Okay, but then to get to the next one, maybe the rule is that you look at the ones that came before it, and then you, I don't know, subtract them and square them. So it'll be, let's say that the rule says take 3, the 4, subtract the 3, and square it. So that gives you a 1. Good. And then the next one is going to be subtract the previous two in this order. So then this would be 1 minus 4 and square it. So that would be 3 squared is 9. Good. Maybe the next one then would be this one minus that one. The next one would be 9 minus 1 squared, which is 8 squared, that's 64. Good. So the rule is subtract the previous two, right, to get the next one on the list. Subtract the previous two values on the list then square them. Right? Is it clear that that's what I was doing here? To get the next one on the list, right? So the first two values are given. You got to get the thing going, right? Because I can't find this number if the way to find it is to look at the previous ones on the list. And like, there is no previous ones. It's, this is the first one. So the first two have to get, you got to get the ball rolling. So the first number, the first two numbers, the first few numbers, a finite number of initial values will be given, the initial conditions. Okay, so then to find the next one, we follow the set of instructions, right? So is it clear that this is what I did? I took the previous two and subtracted them in this order. 4 minus 3, squared it. So that's how I got a 1, right? To find the next one on my list, I took the previous two and subtracted them, 1 minus 4, and squared them. That's how I got a 9, right? To find the next one on the list, I took 9 minus 1, squared them, I get this one, right? To find the next one on the list, it's going to be 64 minus 9 squared, right? So it'll be 55 squared. Clearly, this is going to grow pretty quickly. Good. Okay, well, how do I describe this in math talk? Because you don't want to write down these sentences all the time. So how do I describe the exact same thing? Okay, so let's use these notation values. The third one. To find the a sub 3, I took a sub 2 minus a sub 1 and squared it. Right? That's what I did for a sub 3. A sub 3 was equal to, let me make some more room there. I guess I'll write it over here. A sub 3 was equal to a sub 2 minus a sub 1, and I squared it. Okay, that's how I found a sub 3. Took the a sub 2 minus the a sub 1. Okay, to find a sub 4, let's make it a little smaller here. To find the a sub 4, I took a sub 3 minus a sub 2 and squared it. Right, that's how I got this one. A sub 3, which was a 1, minus the a sub 4. This guy is the a sub 3, is that guy. And this one was the a sub 2, that guy. And then I squared it. To find the a sub 5th one, I took a sub 4 minus a sub 3 and squared it. And that's how I found this one, a sub 5. Good. Okay, well then in general, if I keep going, eventually I'll find the nth one. Let's scoot over here a little bit. If I kept going, dot, eventually there would be the a sub nth one over here, a sub nth one. And how do you find the value of the a sub nth one? Well, you need to know the two numbers that came before it, right? And so sticking to my notation style, right, these are the counting numbers. So if that one is the a sub n, the one that came right before it would be the a sub n minus 1 location. And the one that came right before that would be the a sub n minus 2 location value. Right? And sticking to this formula, the a sub nth value will be found by taking the one that comes right before it, the a sub n minus 1 value, minus the a sub n minus 2 value, and then squaring the whole thing. Any questions about any of this? So this is just an example of what is a recursive one. Obviously, the little rules, the little formulas will all vary, but they all have the same characteristics. It's a sequence, but instead of being able to plug in the location value, like the 4, for example, there's nothing we do to the 4 to get to the 9. I can't square it, divide it, right? There is no set rule that will allow me to map the index numbers, the counting numbers, to the value that is there in their location, right? Someone might say, well, why don't you, the rule could be to multiply the 4 times 2 plus 1. Okay, that works for this one, but that same rule does not work here. If I do the same rule here, multiply the location, 5, and multiply it times 2 and add 1, that doesn't give me 64. Right? So I need one solid rule that works for all of them, that always maps their location to the value on in that location spot. But the way I've described this one, there's no way to do that. However, there is some method to this madness. It's not just random numbers. The numbers are described by the previous values that came on the list. In this case, every nth value can be found by looking at the two values that came right before it. Right? We do something to those values. We subtract them and square them. Any questions about this example at all? No? No? Okay, so let's look at the formal description. So some sequences do not have simple defining formulas like those in the previous examples. The nth term of a sequence may depend on some or all of the preceding terms. The sequence defined in this way is called recursive. Here's an example. Here's another example. Find the first 11 terms of the sequence defined recursively in the following way. So here the capital F is being used to describe our sequence. Right? So we already have the first two on my list. Let's put them over here. And you want the first 11? That's a long list. All right, so the first 11, I'm going to need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so that's a lot of numbers. Okay, so we have f of 1, the first one on my list, the second one on my list, the third one on my list, the fourth one on my list, the fifth one on my list, the sixth one, the seventh one, the eighth one, the ninth one, the 10th one, and the 11th one. I won't go out that far because that's a lot of work. Okay, the first couple are just given, right? That's key to any sequence defined recursively. We got to get the ball rolling because the next one will depend on previous values, so we got to get started. Okay, so here is the recursive formula given for the nth one, right? The nth one is described by taking the nth minus 1, n minus 1th value, and the f of n minus 2th value. So the one that comes right before it and the one that comes 2 spots before it. That's what that means, right? So, for example, f of 3, right? This is where n equals to 3, is equal to f of 3 minus 1 plus f of 3 minus 2. So f of 3 is equal to f of 2 plus f of 1. It means to just add the previous two values. F of 1 is a 1, f of 2 is a 1. This one and this one both map to 1s. A 1 and a 1. So f of 3 is going to be equal to 2. And that's how we get to this next value up there in blue, 2. Right? So now we have the first 3 values on my list. For the sake of getting comfortable with this notation, I'll do a couple more, but it's really not necessary, right? It's a very simple recursive formula, and I'm not going to demand that you do all of this work when you eventually get to this on your test, but it's nice to be able to do it because if the formula gets really, really complicated, you're going to want to do some of this, even if it's not every little step. Okay, so f of 4 is equal to f of 4 minus 1 plus f of 4 minus 2. So f of 4 equals to f of 3 plus f of 2, right? And the f of 3, we just discovered that one. That one was a 2. And f of 2, well, that's still a 1. So this is the 2, and this is this 1 right here. So f of 4 equals to 3. Good. So we'll put it over here. How does yellow look? Probably not very good. Like a brown. Oh. Good. I'll do one last one this way, and then we can just go crazy with the rest of them. So this f of 5 is equal to f of 5 minus 1 plus f of 5 minus 2. So f of 5 equals to f of 4 plus f of 3. F of 5 is equal to f of 4, which we just discovered as this 3, plus, and then the f of 3, which was a 2. So f of 5 equals to 5. Good. 5. So there, we got the first 5 numbers now. Almost there, right? But again, you don't have to do this much crazy work every time. Sometimes the pattern's pretty easy. Just add the previous two. So I can easily tell that the next one is going to be the sum of these two, which is going to be equal to an 8. And the next one is going to be the sum of these two, which is going to be equal to 13. And the next one's going to be the sum of these two, it's going to be 21. And the next one is going to be a sum of these two. Right, so it's growing pretty quickly. 34. And the next one's going to be a sum of these two, which is 55. And the next one is 89. Any questions? I'm sorry, I didn't catch that.
How did you know F2 would have been 1 also?
Oh, it's given to you. Find the first 11 terms of the sequence defined recursively, and f of 1 is 1, f of 2 is 1.
Oh, okay. I see it. Thank you.
Yeah. You know, that's a key characteristic of these types of recursively defined sequences. They got to get the ball rolling. They got to get you started with the first couple of them, maybe the first 2, the first 4, the first 5, because the next one is described by numbers that came before it. So there's no way to do it if you don't know the numbers that came before it, right? So the first few, at least one, or the first a couple of them will be given to you, and then you got to keep going with the recursively defined sequence. Okay, so the recursively defined sequence has a big flaw in it, though, right? Because if I wanted to find, if I said, okay, this is a lot of fun, keep going, you found the first 11 of them, that's a lot of fun. Let's find, I need the 100th one now. Keep going. I need to find f of 100, the 100th number on this list. Well, the only way to find that 100th number is to know the 99th and the 98th number. Right? And the only way to know 99th value is to know the 98th and the 97th value. And the only way to, right? So the point is, you can't just skip to some number in the future and find that number. The only way to get there is to build up to it. So it's not as useful as the closed formula that we saw before, where you can just jump to the 100th number by plugging in 100 into the formula and out will pop out the answer. Good. So from that perspective, recursively defined sequences are inferior to sequences defined by a closed formula. So you might wonder, well, why do we work with these? Well, because we don't really have a choice, right? This isn't something we've invented. This is just something we've noticed in the universe. This is just the way it works. There are some sequences that do not have a closed formula, but do have some sort of a recursively defined formula. Now, there are some sequences that have both. You can describe it recursively, or you can find a closed formula for it, and some sequences that don't have them both, right? So this is a very famous sequence called the Fibonacci sequence. It occurs in lots of areas of math and science and in the universe. There's some stuff that just kind of happens to follow this pattern. So it's important, useful, fun, interesting. But as far as we know, there is no closed formula for it. But, I mean, the question is there no closed formula? Like, there can never be one? Or maybe we just haven't found it yet, right? I don't know. So maybe somebody in the future discovers some awesome, great formula that maps out the Fibonacci sequence. And then, of course, that person will be rich and famous. Good? Questions? No? Okay, so any questions on recursive formulas? No. Let's see what the author did. So same as what I did. So f of 3 equals to the sum of f of 2 plus f of 1. F of 4 equals to f of 3 plus f of 2. Okay, so you can slowly build out your sequence until you get to all the 11 numbers that they wanted. So this is called the Fibonacci sequence, named after the 13th century Italian mathematician who used it to solve a problem about the breeding of rabbits. Right? So breeding rabbits somehow is connected to this Fibonacci sequence, the way a group of rabbits will grow in a population. Now I think that, there's probably some tweaking that happens there. I don't think you want to start with one rabbit and one rabbit. That seems weird, because then, anyway, sorry, there's a big truck going right by my window. Anyway, so maybe like 1,000 rabbits, and then you come back in some term, some time later, some unit of time later, you come back 1 month later, and 1,000 rabbits is still 1,000 rabbits. And you come back 1 month after that, by the 3rd month, now you have 2,000 rabbits. So, those rabbits had babies. and then after another month or some other fixed unit of time, we come back and now there's 3,000 rabbits, and now there's 5,000 rabbits, and now there's 8,000 rabbits, right? So the rabbit population can be modeled to grow in this way. Of course, that's without any other restraints, right? Because they'll grow in this way, say just out in nature, until they run into a problem, right? So if they run out of food, they run out of space, or a predator comes in, or a virus or something, then their population will then decrease, right? But anyway, there's a lot of things that Fibonacci sequence can be used, can be applied to. Okay, any questions at all so far then? So far we have sequences. Sequences are indexed by the counting numbers. So we have closed formulas for some of them. We have recursive formulas for some of them. Good. So you might be asked to expand the recursive formula, or you might be asked to find the recursive formula given the numbers. Okay, now let's look at the partial sums of a sequence. Something else that we might want to do, that we often want to do, particularly in calculus as we prepare to get into calculus, is that when we're given a sequence, we want to think about what happens as we begin to add them in this way. So let's say that we're given the sequence a sub 1, a sub 2, a sub 3, so on and so forth. We want to create a new sequence. A new sequence, which here we're using the letter capital S to represent this new sequence, where the first number on my new sequence is just equal to the first value on the given sequence. And then the second value of my sequence is the sum of the first two values of my original sequence. The third one is the sum of the first three and the sum of the first four, and so on and so forth. So this itself is a new sequence, but it's a sequence of partial sums. Good. So S sub 1 is called the first partial sum, S sub 2 is called the second partial sum, and so on until we get to the S sub n is called the nth partial sum. Good. Let's expand this with a simpler problem before we get into their first example. So let's like mimic this with an example. So for example, if the original sequence a sub 1, a sub 2, let's just say that it is the even numbers. No, let's not make even numbers. Yeah, that's fine. Let's just make it the odd numbers. So here's the sequence: 1, 3, 5, 7, 9. Right, so here is a sub 1, here's a sub 2, here's a sub 3, here's a sub 4, here's a sub 5. Right, so here is a sequence that's given. Right, that's this. And what we're going to do is we're going to create a new sequence where the first value of my sequence is equal to a sub 1. That's just going to be 1. S sub 2 is the sum of the first two on my sequence. That's 1 plus 3. That's going to be 4. S sub 3 is going to be the sum of the first three values on my sequence, which is equal to 9. S sub 4 is the sum of the first four numbers. 3 plus 5 plus 7 is equal to 16. Good. And so on and so forth. So then my new sequence is going to be 1, 4, 9, 16, dot. Right? So this is a new sequence. So this is S1, this is S2, this is S3, and this is S4. Good. So now the original sequence, as I presented it to you, there's a formula for this, right? It's just the odd ones. So this one is the nth value on my list is just going to be equal to, I'll just put it over here, is equal to 2n minus 1. Right, that's the nth one on my list. Good. Okay, and same thing over here. There's a pattern that's happening here. The nth one on my list, way out here, the nth one on my list is, well, it's that. There's not a very easy way of describing it. It's just a1 plus a2 plus a3 plus dot, all the way out to a sub n. That's what the nth one is. Okay, good. Good. So the sequence of partial sums is a brand new sequence, which is defined by adding the first n numbers of an underlying sequence that's usually given to you. Good. Any questions? No? Okay, so let's look at another example. Find the first partial sums of the nth partial sum of the sequence given by a sub n equals to 1/2 to the nth power. Okay, so first let's begin by expanding this sequence a little bit. Let's find the first value on my list. Let's find the second one. Let's find the third one. Let's find the fourth one. Let's find the fifth one. That's pretty good, right? And then we know that the nth one is the formula. So this is 1/2 the power of n. Okay, so this one's going to be 1/2 the power of 1. This one's going to be equal to 1/2 power of 2, 1/2 to the power of 3, 1/2 to the power of 4, and 1/2 to the power of 5. Right? And so I can write it down in a more simple way this way. The first one on my list is a half, then a 4th, then an 8th, then 1/16, then 1/32, dot, 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 dot. Right? We'll leave it alone for that. So here's my underlying sequence. Good. So now I want to find the s sub 1 value. Okay, that's just the sum of the first one. Well, that's just a half. And then s sub 2 is going to be equal to the sum of the first two. It's going to be 1/2 plus 1/4. You need a common denominator. That's going to be to multiply this by a 2 over a 2. So we'll end up with 2/4 plus 1/4, which gives you 3/4. Okay, so the second one on my list is going to be 3/4. The third one on my list is going to be equal to s sub 3 is equal to 1/2 plus 1/4 plus 1/8. Common denominator is going to be that 8, so let's multiply this by 2 over 2. Multiply this by 4 over 4, and we will end up with 4 over 8 plus 2 over 8 plus 1 over 8, which then gives me 7 over 8. Good. And then finally the fourth one is that find the first 4 partial sums. The fourth one on my list is 1/2 plus 1/4 plus 1/8 plus 1/16. Right, the sum of the first 4. And the common denominator is that 1/16, so let's multiply this by 2 over 2, multiply this by 4 over 4, and multiply this by 8 over 8. And I'll have my values of s sub 4 will be equal to 8 over 16 plus 4 over 16 plus 2 over 16 plus 1 over 16, which equals to 12, 14, 15 over 16. Okay, so I already have my first 4 values. The first one on my new list is going to be 1/2, followed by 3/4, followed by 7/8, followed by 15 over 16. So let's write down those values. So here was my underlying sequence, a sub 1, a sub 2, a sub 3, right? And now s sub 1 is going to be equal to 1/2. That's s sub 1. S sub 2 was 3/4. S sub 2 is 3/4. S sub 3 is going to be 7/8. And finally, s sub 4 is 15 over 16. S sub 4. Okay, well, a lot of what we do in math is look for patterns, right? So a very nice little pattern begins to appear. Just based on this little pattern right here, can we do a pretty good guess of what the next one's going to be? Right? Just based on this pattern. Notice that it's always the case that the numerator is 1 less than the denominator. Right? 16, this one's 15. 8, this is 7. 4, this is 3. 2, this is 1. It's always 1 less. Or you can look at it the other way around. It's always 1 more. 1, and we add 1, we get to 2. 3, we add 1, we get to 4. 7, we add 1, we get to 8. So really, all you have to do is find a formula that connects its location values, the numbers, to either the numerators or to the denominators, and then you can tweak that by adding or subtracting 1 to get to your answer. Okay? So if we look at the denominators, 2, 4, 8, 16, well, that's just the powers of 2, right? So there's a nice pattern that emerges there. So I'm going to guess that the next one here is going to be equal to 2 to the power of 5 in the denominator. And that's going to get me to 32, right, because it's powers of 2. And then in the numerator, it's always 1 less. So I'm just going to say that the numerator is 2 to the power of 5 minus 1 as well. Good. So they didn't ask for this, but this is a nice little pattern here. So why not do that? And then, well, okay, as long as we're establishing the pattern, then as we keep going, the nth one, well, the pattern is going to be that it's a fraction where we have 2 to the nth in the denominator and then 2 to the n minus 1 in the numerator. Good. Any questions? Any questions? Any questions? No? 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 This looks weird because now this looks like a giant fraction. That's all weird. So let me rewrite that this way. I don't want to write it like that. I'll just say s sub n is equal to a giant fraction where the denominator is 2 to the nth power and the numerator is 2 to the nth power minus 1. So look, we were able to get a nice closed formula for the sequence of partial sums in this case. Any questions? Okay, let's see what the author did. Find the first, okay, so we found that, and then 1 3/4, and then 5 15/16. Notice the value of partial sum, the denominator is powers of 2, and then 1 less for the numerator. Okay. So in general, the nth partial sum is exactly what I got. And then you can simplify this by breaking this up as 2 to the nth over 2 to the n minus 1 over 2 to the n. And that simplifies to this. And then we can also just map it all and see a pattern. Right, so the original values, the a sub 1, a sub 2, a sub 3, a sub 4 values, map this way, whereas the sequence of partial sums are mapping up to here. Particularly when we see it in this notation, we can see what's going to happen in the long run. Right? As n gets bigger and bigger and bigger and bigger, this denominator is going to get bigger and bigger and bigger. Right? So 2 to the 8th power, 2 to the 16th power, 2 to the 20th power, 2 to the 100th power. Right? This denominator gets huge. 1 over a very large number becomes a very, very small number. Right? And so as n gets really large, we end up with 1 minus a very small number. Infinitely small number. So as n gets really large, the output of this is going to become really, really close to 1. Right? So this is going to have a horizontal asymptote at y equals to 1. These outputs are going to get closer and closer and closer to 1, but never equal to 1, and it's never going to be bigger than 1. It's just going to get closer and closer and closer to 1. Does that make sense? Yes. So there will be a asymptote here. Let's see if this looks good on Desmos. Let's see if we create a table and we have x, well, let's do n, and then we have 1 minus 1 divided by 2 to the power of n. Okay, and we start off with 1, that maps to a half, 2, that maps to 0.75, 3, then 4, then 5, 6, 7. Right? Do you see how, plugging into here, I get all these outputs, and then if I graph them, I get 1 comma 0.5, 2 comma 0.75, 3 comma 0.875, right, and so on and so forth. But they're not growing out of control. As n gets larger and larger, this part gets smaller and smaller and smaller. So as n gets larger, this output becomes closer and closer to 1. Look, at n equals to 7, it's already at 0.9928. So eventually they approach a horizontal asymptote at y equals to, what happened to the, y equals to 1, right? So these little green guys get infinitely close to that red line, and even though it almost looks like it is equal to that, it's not. If you zoom in, zoom in, zoom in, eventually you see that the green dot is not actually on the red one. Okay? And it might look like it's it. Right, so that's what this is describing. S sub 1, S sub 2, S sub 3, S sub 4, S sub 5. Any questions, any questions, any questions, any questions? Okay, okay, so we want to refresh our memory on sigma notation that helps us express an infinite sum. That's what sigma notation is. So given a sequence, a sub 1, a sub 2, a sub 3, so on and so forth, if we want to describe how to add the first n numbers, we can write the sum of the first n numbers using sigma notation. And that's what this is. Right? This notation means that we want to add a sub 1, a sub 2, a sub 3, a sub 4, dot, 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 dot. This tells you where you're going to begin your counter, right? So the index here is the k. So we use this little guy here, this little counter as k. And so it will change starting at 1 and ending at and including this number up here, this value up here. And it's always a sum for this notation, right? This giant sigma means it's an infinite sum. Good. Good. Okay, so the left side of this expression is read as the sum of a sub k from k goes from 1 to k equals to n. The letter k is called the index of the summation, or the summation variable, and the idea is to replace k in the expression after the sigma by the integers 1, 2, 3, dot, 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 all the way out to n, and then add the resulting expressions, arriving at the right-hand side of the equation. So this giant sigma tells us to add. The k tells us where to begin. K equals to 1. The k equals to n tells us where to end. Be careful because it doesn't always have to start at 1. It could be a different value that goes in there. Right? And then if there's more than one instance of the a sub k, then you would apply it to all of them. Good, good, good. Okay, so here's some easy examples. Find each sum. And so just expanding these. So for part A, we want to get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right? That's what this is. And I know to stop there because this tells me to stop when it equals to 5, right? So replace the k by a 1. I got a 1 squared. Plus, replace the k by a 2. Replace the k by a 3, and so on and so forth. Oops, I guess I don't need that. So now we just simplify it and get an answer. So this becomes 1 plus 4 plus 9 plus 16 plus 25. Good. So let's see, that's going to be 5. 5 and 5 makes it 30, 39, 45, 55. Good. Okay, for B, well, it doesn't start off at 1, it starts off at 3. So this would be 1/3 plus 1/4 plus 1/5, and that's how I know where to stop. Right? And notice that the index in this case was a J, not a K. So we have to be careful about what letters we use. Okay, common denominators here. Let's see, it looks like it's just going to be a multiplication of all of them. 60. Good. So 3 times 2 times 5. Yep, 60. I don't know. Okay. So multiply this by 12 over 12. Multiply this guy by 15 over 15. Multiply this guy by 20 over 20. So we'll get 20 over 60 plus 15 over 60 plus 12 over 60. Good. That's 35/47 over 60. Questions, 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 questions? Okay, C says to start off at 5, so it'll be 5 plus 6 plus 7 plus 8 plus 9 plus 10. Start off at 5, end at 10, and all I'm doing is replacing the k index value by a 5. Good, so that's 11, 18, 26, 35, 45. Good, 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 good. D is a little tricky because there is no index, right? Here is the index I, and there is no I. So what we do with that is that, well, when I equals to 1, we just get a 2. Plus I equals to 2, well, we just get a 2. When I equals to 3, well, we just get a 2. Right? We have to add all of them, and we know we keep going until I equals to 6. So this is I equals to 1, I equals to 2, 3, 4, 5, and 6. So this is going to be 2, 4, 6, 8, 10, 12. Any questions? Should have put them here. So this one we got was 55. This one we got was 47 over 60. This one equals to 45, and this one equals to 12. Good? Questions, 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 questions? No, 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 no. Let's see if the author did the same thing.
I go over C again, please.
Sure. Let's go over here. Oops. Over C, you said? C is this one. So it's the Riemann sum starting at 5 through 10 of this, which is just k. So the first one comes by replacing the k with a 5, plus, then a 6, plus, then a 7, plus, then an 8, plus, then a 9. So we start at 5, end at 10, and we always add them, right? Because that's what this sigma notation is telling us to do. So I just had to add all of these, unless there's something wrong with the summation. That's 11, 20, 30, 37, 45. Yeah, I think so. Good. And is it okay with D? I think D is the trickiest one, right? Because there isn't even an index there. So like, what the heck do I do? There is no I. Right? So what we do by default is just add the constant that's there.
So for D, we just go ahead and just use the, I guess, the 2 there 6 times.
Correct.
Thank you.
Good, good, good. Okay, here. So let's see what the author did. Probably the same, hopefully, unless I did some wrong. Okay, so for A, right, we're replacing the K value with 1, then 2, then 3, then 4, then 5, right? And every time we were squaring them, so we get these. Good, 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 good. And then we get that. And then for B, we start off at 3, so it's going to be 1/3 plus 1/4 plus 1/5. And here's C and here's D. Good, 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 good. Okay, graphing calculators for this, I don't worry about that. How about one more example that's a little more complicated, just to point out how that expression is given. So let's say that we have an expression and we want to use any number. You know, n is also very popular. So let's say n goes from 3 through 7. And the thing is that this index value can happen more than once. So I wish there was an example that had more than one of them. So for example, it could be that it is 1 over n plus n squared, for example. So this is letting me know that I want to do 1/3 plus 3 squared. That's when n equals to 3, plus 1 over 4 plus 4 squared, plus 1 over 5 plus 5 squared, right? So we just keep going with these summations. Summation, summation, summation. At each one of these little intervals, we're replacing the index, in this case the letter k, the index variable n, with a 3. And then we just keep going. And we don't stop until we get to the stopping value there, which is equal to 7 in this case. So we got to include a 1 over 6 plus 6 squared, and then a 1 over 7 plus 7 squared. Good, good, good. Sometimes, you know, just to kind of explore more on this notation, sometimes it might not be a pretty little number where it ends. They might just give you some other letter there that ends at, you know, K or something. All right, well then, if you just want to explore this and expand it, you would say this, you know, but then you would leave a kind of a dot, 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 you know, continue in this pattern, dot, 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 and then continue in this pattern until you get to the stopping point, which is K. So you'd say this, right? That would be this one. So plus that. Good. Okay. All right, but let's go back to it being a number. Okay, so let's go back to this being some number. So let's say that it's just equal to 6 again. So let's say it's just 6. Okay, so let's just erase these guys. The other thing that kind of confuses people is there might be another letter in here. Like there might be an X. Okay, all right, well then leave it alone. The index is only referring to the letter N. So if there's an X in there, then just leave an X right in there. Okay. So then, I mean, we could simplify this just a tiny little bit. 1/3 plus 9x plus 1/4 plus 16x plus 1/5 plus 25x plus 1/6 plus 36x, right? So if there are other letters running around in there that are not using this little index guy, then just leave them alone. Good. Questions, 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 questions? No? No? Okay. Okay, I think that that's all we have here for this. Okay, so we can use technology to do some work with these, but I'm not going to cover that. I don't think you really need it. So let's just move on past it. Okay, some properties of sigma notation, right? So if we are doing the sum of a sub k plus b sub k, like this, there's two different sequences indexed by k, and notice that the index of the summation is a k, then we can find them separately and then add them together, right? That's what this is saying. Same thing if we're subtracting them. If we're subtracting two of them, then we can do them separately and then find their differences. And this last one is saying if there's a constant that we're multiplying by all our takes k values, then we can factor out that constant. So what this means, let's do an example for number 1. So like for number 1, as an example of what that's saying. Let's say I'm asking you to do the sum of k. Man, this thing is not happy now. Why are you so upset? Number 1. Let's say that I want to do the sum as k goes from 3 through k goes to 5. It's just 3, 4, 5, just a few values. And I have some formula in k, like k squared plus, I don't know, square root of k. Say I have that. So this can be broken down by number 1. This is saying that what you could do is separate this as this one, k squared. So find the answer to this, plus, and then separate from that, and that 50 is in the terrible spot, k equals 5, and k equals 3 of square root of k. Right? That's what this is saying. If you have a really complicated statement separated by an addition or a subtraction, then you can separate these this way. Right? Same thing happens if instead we have a subtraction there. Well, you can just replace it by a subtraction there. Good. 1 and 2. And then the last one says that if there's a constant in there, we can just pull out the constant. So the third one is saying, for example, that if I have this, I don't know, k squared, but I also have a 7 there, summation as k goes from 2 through 9. So I'm going to do k equals to 2, k equals to 3, k equals to 4. Okay, so that one is saying, well, there's this constant here that we're multiplying, so we can just put it on the outside and then figure out what this is. K squared as k goes from 2 to k equals 9. Figure out what this is, multiply by the 7, and you'll get the same result as this one.